Okay, so let's start today's week 9, and you are watching the live session of the NPTEL course Electromechanical Energy Conversion and DC Machine by Professor Bhim Singh. And I am Subhadip Chakraborty, a PMRF scholar in the Department of Electrical Engineering, IIT Delhi, and I will be your TA for this session. So today's week we will be discussing some concepts and numericals related to energy conversion, especially for the electromechanical energy conversion perspective, and also some concepts and numericals related to DC machines. So I welcome you all to this live session, and we'll go ahead with the session. So as you know, the timing of this session is every week Tuesday 7 p.m. to 9 p.m. and we are in the week 9 of these live sessions of the NPTEL course. And today's week discussion is related to electromechanical energy conversion and DC machine, right? So just starting electromechanical energy conversion, what do you understand by the term electromechanical? That it is related to two forms of energy, right? Electrical and mechanical. And by the term energy conversion, you understand that it is related to conversion of one form of energy to the other form. So electromechanical means either from electrical to mechanical or mechanical energy to electrical energy. Now you know that electrical energy is of the form, if you apply some voltage, you get some current, and there is some energy storing elements and energy dissipating elements in electrical engineering, right? So if you can convert those electrical energy stored in the form of electrical fields or electrostatic fields or magnetic fields in some way or the other to a mechanical energy. A mechanical energy means in some forms of rotation or some force or some movement, right? Because mechanics or mechanical energy is really all related to some kinds of motion, right? So some rotation or some force, either ways, linear or translatory or rotating forms of motion, or it leads to actually mechanical energy, right? Generation of mechanical energy or vice versa, conversion of those forms of mechanical energy either from translatory or rotational forms into back into your electrical form. So if you can do that, we term it the energy conversion process. And why everyone wants to convert everything or every forms of energy into electrical is because it is easiest to transform. So electrical energy is easiest to transfer, right? Easiest to transfer as well as store. As well as store. That is most efficient of all forms of energy conversion, right? So that's why electrical energy is mostly preferred, and you use electrical energy and electrical equipments everywhere, from day-to-day appliances as well as in your industrial as well as residential usage, right? So it is a very important topic which guides you through the working principles, how the mechanical energy is getting transformed. That is how motion is getting transformed into some forms of electrical energy, either in forms of voltage or some generation of some forms of EMFs, right? How it is happening by the laws of physics, and how we can utilize it in the day-to-day appliances, right? So coming to the electromechanical energy conversion process, as I told you, it is one form of energy conversion which relates electrical and mechanical systems and energies, which has a coupling, which goes through a process of coupling to transform in from electrical to mechanical or from mechanical to electrical or vice versa, right? So it is related to electrical and mechanical energy, right? And obviously if you have mechanical energy producing devices, you have a mechanical system for that, right? And obviously for electrical energy to get generated or utilize it, you need some electrical equipment. So have a electrical system on one side and a mechanical system on one side, and in between you have some coupling field or some forms of media through which the energy is getting transferred, right? So that coupling field exists, which helps us to convert the electrical energy of the electrical system into the mechanical energy, which is utilized by the mechanical system, or the mechanical energy from the mechanical system back to the electrical energy to be utilized by the electrical system. So that form of energy conversion exists, and we therefore study the electromechanical energy conversion. So you know that the electrical energy is supplied, for example, by a source, then that energy will be splitted, that is into the coupling field and then the losses, right? So that energy which you actually deliver, let's say from the electrical side, in order to convert to the mechanical side. So that complete energy will be stored in a media, which you have termed as the coupling field, right? So that energy is first stored into some medium, and the remaining part is lost, right? Because in electrical systems also, there are conduction losses. So in order to store some energy in the field also, in order to generate that process, you need to lose something, right? Because purely lossless energy conversion cannot happen, because in mechanical systems, as well as in electrical systems, there are losses. So first you have to go through that losses and supply that losses. So you have some forms of energy, electrical energy, and you have to first meet the losses, like the air gap power in induction machine you must have gone through. So there are some losses, and then you have the field, right, coupling field, which stores the energy, and that energy is ultimately converted back to your mechanical energy, like forms of rotation or forces, anyway. And then this is generating the actuation, right? Either translatory or rotatory motion, or what forms of actuations you have in mechanical system, some force or some torque is generated. So from electrical domain you go to mechanical domain, and again it is possible that from mechanical you again spend some losses, some mechanical losses, because in mechanical motion or mechanical movement or mechanical rotation you have to go through some losses. Apart from that, that energy, that kinetic energy you call, or whatever you call, that energy stored in that mechanical system is again converted to the coupling field, and that coupling field is again transferring that total energy, converting it to electrical energy for utilization. So this coupling field actually facilitates the movement of energy from one form into another. So it is facilitating the transfer or conversion of energy. So this field is generally in electromechanical systems, this field is a magnetic field. That can also be an electrostatic field, but please understand that a magnetic field is generally in all machines, electrical machines I am telling, we generally take help of magnetic field for the coupling field or for the media which will assist the transfer of power, active power, or the conversion of active power from the electrical terms to mechanical, or mechanical to electrical. You have seen everywhere that throughout the process, or whatever electromechanical systems from an electrical engineer's perspective you use, you mostly take assistance of the magnetic field as the coupling media. Can you tell why not electrostatic field? I just want to hear from you. This is a very important point, and I think this should be very clear in your mind. I told you that there should be some media or some field which helps in the transfer of mechanical and electrical energies, right? Now, by Maxwell's equations in class 12th physics, you know that a changing electric field can generate changing magnetic field, and a changing magnetic field can generate changing electric field. And if you have some energy, you can convert it to some form of force, right? If you have some energy, you have some work done by work energy theorem. So del energy is nothing but work done, and work done by the displacement can give you force. So this is mechanical parameter. Again, by Maxwell's theorem, you also know that if you have some time varying electric field or time varying magnetic field, you can just generate some voltages, right? So a time varying electric or magnetic field can correlate and can generate voltages, right? So this is a electrical parameter. So in both way, both electric, that is electrostatic fields, as well as magnetic fields can help you attain this conversion process. But why we take the help of magnetic field as the coupling field and not electrostatic field? See, both are lossless. Electrostatic field is also lossless, right? There is no loss happening. Obviously, loss in the mechanical and electrical sides are happening, but the field itself is not consuming any active power. Please try to understand. It is delivering whatever it is getting, it is exchanging the processes, right? As long as it is maintained, the electrical side or the mechanical side is maintained, that is the rotation is maintained, or from the electrical side you are trying to convert, then the voltage is maintained across the plates, which will generate the electric field, right? Those things are okay, but it is not itself consuming any power. But still, why we don't prefer the electrostatic field as the media for your electrical to mechanical? It is possible. You have some charged plates, you apply some voltage, and you can generate motion, right? Translatory motion of any charged particles. Now, why not we generate the motion or in other forms, we can generate rotatory as well as translatory motions, right? Because that will create one field, and coupling of two fields can generate torque, right? You have learned how two dipoles can generate torque, or two charged plates can generate repulsive or attractive forces. We can generate mechanical forms of energies with electrical systems or electrostatic, with the help of electrostatic field, but not, we don't generally see electrostatic fields being utilized in electromechanical systems like the electrical machines. Why so? Why we take help of magnetic field as the coupling field? So this is generally a magnetic field, right? Magnetic field generally. Just unmute and tell why generally we take help of magnetic field for the energy conversion media. So as you can understand, this is energy stored in some forms. Now I am asking you why magnetic form. So electric to magnetic form, actually it is getting stored, because you know a moving charge creates a magnetic field, and a current also generates some forms of flux, and it is nothing but the participation of some parameters from the electrical domain leading to the formation of a magnetic circuit, which is coupling your total system, and with the help of the magnetic circuit, actually the energy conversion is taking place from electrical to mechanical. No, so why not electrostatic? You can just unmute and tell me. Then we'll go forward with more discussions. So as you can understand, to create a significant amount of electric field, you need a large amount of voltage, which is not feasible, and it is also big in size and also costly, and you cannot use it for day-to-day appliances. But with the help of by increasing the number of turns, you can generate significant amount of magnetic field such that you can get significant amount of torque, because electrical machines are used as motors or generators. Now what is the purpose of a motor? To generate some forms of torque. Now if the torque is not utilizable within the general usable limits of voltage and currents, then why will the user use it? They will not use it. So the advantage of magnetic field is that within a very small system or a very small size of a machine, I can tell you, it can generate a significant amount of field by increasing the number of turns, so that by passing some current with a nominal current and voltage, you can generate significant amount of field intensity, which is almost sufficient to generate the amount of torque you need, or the amount of force you need to rotate your, maybe your mixer grinder or something, right? Whatever appliance you see in your day-to-day common appliance, that should be in the workable range of voltage and current, right? It should not be in kV or some higher voltages. But you cannot generate such a significant force using small voltages, because electrostatic fields are very weak in small working voltages, so they are not very user friendly. And as well as to generate a high voltage and then to use it for an application, you need to generate insulations also for protection purpose, and those are very costly for higher amount of voltages. But with current, even with by passing a very small current through a ferromagnetic material, you can generate significant amount of mmf by increasing number of turns, so that you can generate a torque, significant torque. So that is the advantage, right? Both economic as well as your what I can say technical advantages are there using the magnetic fields, right? So as I told you, from the mechanical side, if you submit some forms of energy, just W you can consider some forms of energy, right? Because by work energy theorem, what is work? Work is nothing but change in energy. You have learned in class 12. So that is also spent in the coupling field and some forms of mechanical losses. Similarly, as I told you in the electrical term. So if you start from electrical, yes, please tell me what you are trying to tell me. You can just unmute. HV is by capacitor. I can just read what you typed in the comment box. I think you typed. Yes, you are telling HV, high voltage, is by capacitor and not. See, there are, the perspective I am telling you is for electromechanical energy conversion. There are capacitors used in both power systems as well as in electrical machine. Your fan also uses a capacitor, but that capacitor is not used for the energy stored or coupling field. That capacitor is used for some different purposes. In single phase induction machine, you use capacitor, but that capacitor is not the reason of your coupling field. The field which you use to transfer the power is never electrostatic. In whole electrical engineering, you do not use a particular capacitor to transfer energy. Do you understand what I tell? A bulk amount of energy transfer is not done through capacitors. It is done through magnetic fields, because bulk amount of power can be done with a very small, by pushing or creating a very small MMF, right, through a small amount of current, because the number of turns you can increase so that you can create that flux. And flux does what? Changing flux creates voltages. So it is very lossless as well as efficient as well as compact. So power transfer from electrical and mechanical among vice versa, that thing, the coupling field I am telling is of magnetic media. But yes, in theoretical terms, you can use also electrostatic. You have done problems also, right, like that. But generally, in day-to-day electrical engineering applications, in power systems perspective, you can see the bulk power transfer is not for electromechanical energy conversion. I am telling you, for electromechanical energy conversion, bulk power transfer is never done by using electrostatic fields. Obviously, if you use power electronics equipment, in power electronics equipment, like you are using a Shook converter. In Shook converter, there is a energy transfer capacitor sitting in between. There, the active power is transferred through capacitor. That is a different perspective. Why you do that? You want to change the levels of voltages, right? In a Shook converter. So that is not a electromechanical energy conversion. There is electrical to electrical. Electrical to electrical, you can use both inductor and capacitor. No problem. That is a different perspective totally. But for electromechanical energy conversion process, I need to have a good coupling field. I need to generate that coupling field, which will assist the conversion process from one energy form to other. Now that field is easily created by electromagnetic field, or you can say simply magnetic field, by generating flux through a very small current. Because that is economic, na? That's why engineers design the total electromechanical energy conversion machines or systems using magnetic fields. That is economic. But in electrical engineers perspective, completely electrical to electrical energy transfer form, you can use capacitor. That is different. Okay. So high voltage and all those shunt compensation or whatever you say, reactive VAR compensators, you use capacitors. That is a different perspective. That is for power factor correction and all those things. Energy coupling generation or coupling field generation always done for electromechanical systems, always done through magnetic media, because it is economic. It is very easy to create in a compact shape, a compact form, through a very low cost device, right? What is the price of a core, right? Small core. Because through a small core, you can generate kVs of voltages like in your distribution transformer, right? And also the copper requirement is very small. With very small current, you can generate flux to generate workable voltages. So they are economic actually. That's why we take the help of magnetic media. They can be easily generated by just multiplying number of turns. In place of 100, if you do 200, you get double the voltage. See how easy it is to create or generate such fields, right? And the application is also vast. In complete machine, you will be using magnetic fields, right, for the electromechanical energy conversion. So as you understand, after the losses, we have the coupling field which stores the energy, either magnetic or mechanical or electrical, in magnetic forms. Because what you know by the physics experiments, what you know, that what is the fundamental principle working behind all of this energy conversion process is that a rotating conductor carrying current can generate changing magnetic field, and that is the whole purpose of the electromechanical energy conversion process. Because you know what, that a changing magnetic field will generate voltages, right? A changing magnetic field will generate voltages, because if you are changing flux, it will generate voltage. Now changing flux can be done by two forms. Either your electric field is changing with time, which is changing the flux, or what, or your mechanical relative motion. There is relative motion, right, mechanically, which is actually leading to changing flux. So this coupling field needs to be seen from the conversion port. So there is a port, there is an input port, there is an output port. Input port, you give one form of energy, output port, you take another form of energy. But the input port should be impressed upon with the energy, and to the output port, the energy that you impressed in the form of stored in the form of coupling field should be varying with respect to some forms or the other, right? So this flux, which is the source cause of the generation of such coupling fields, sees a changing some forms of relative motion if you are converting mechanical to electrical, and it generates electrical. And if you are giving electrical, then it can generate mechanical, because what is the principle? That force is generated, what? Force is IL cross B. Similarly, you have a current, you have a flux being produced due to the current in the electrical side, and you get a mechanical torque, you get a rotation. So everything is working based on this magnetic media. The magnetic media is being formed, and that assists the active power transfer. But please remember, coupling field itself does not consume any power. Coupling field itself is not consuming any active power, right? But to keep the coupling field working, you have to continuously force the electrical side or mechanical side process. Without the mechanical side excitation, you cannot get electrical energy. Without the electrical side excitation, you cannot get the mechanical energy, because that forcing input is actually forming the coupling field, either from the mechanical side or from the electrical side. Please try to understand. So coupling field itself is not consuming active power, but it needs to be maintained for active power transfer. It needs to be maintained by active power for active power transfer. Look, these concepts are very important to start the machine, right? So as I told you, just apply the energy balance. You can see whatever energy you are giving, that is getting splitted, and remaining amount of energy is stored. We say that it is stored and then converted into the second form. So if you give mechanical, you get electrical. If you get electrical, you get some forms of external work you are giving in the form of mechanical energy, and you get the work done out of it. So as you understand, it is basically balancing of energies, right? So in the mechanical system, you have the coupling field and you get the electrical, and vice versa, right? This is completely self-explanatory. I gave you the crux of it, right? So let's go to the derivations, which are very important and will help you solve most of the problems that you see. Okay. So up to this, you are with me, right? Up to this, there is any doubt, you can just ask me, or I can just go ahead with the derivations, right? Up to this, you are all with me. Please unmute and just let me know, because these sessions are meant to be interactive, and if you participate, I will also feel that okay, you are listening. Okay. So let's now jump into some quantitative formulations, so that this concept becomes more clearer and you can use these concepts to solve problems, right? So we are trying to derive some expressions to quantify the energy stored in this coupling field, because I already told you that the coupling field is of magnetic form, right? So what is the strength, or what is the energy stored? So we can all quantify, right? So we define some terms which I have already explained in the previous week also, that the flux density, magnetic flux density. Obviously, we are talking about magnetic circuits, right? So I told you that magnetic flux density, it is nothing but flux per unit area. And I told you by Ampere's law also, you must know that this magnetic field intensity is nothing but, can you know, do you know? This is B by mu. It is defined like this. And mu is the permeability, right? And by Ampere's law, you can just quantify integral H dot dl equal to Ni. What is Ni? It is mmf. These terms you must know by now. So we try to quantify the energy stored of a magnetic field, right? Magnetic field, it is defined as half into B into H. Now where it came from? It came from here, right? That what is the energy stored? So what you know? What is energy? Energy is voltage times current. Now you already know that due to saturation, flux versus current waveform is like this. Now if this is n times phi, I can tell, because the total flux linkage I can say, right? So lambda versus I curve looks like this. And what you also know is that E into I is nothing but integral EI dt is nothing but energy. Energy I am writing as W, because by work energy theorem, change in energy is work done. So I quantify by W, and then energy is d lambda dt. because n d phi by dt is nothing but EMF induced by Lenz's law. So you can just plug everything in. So what is it? D lambda dt. E is d lambda dt. So d lambda dt, as you see also here, d lambda dt times I times dt. So integral d lambda dot I or I d lambda is nothing but energy stored. So it came from here, that take a small lambda and then try to integrate, and this area under I versus lambda curve. So this area is nothing but the energy stored, right? So this and the reverse converse of it is the co-energy. The co-energy does not have any practical significance, but you can use this form to derive the torque and force expressions, right? So how you can derive force? I told you force is what? F dot dx is nothing but energy, because energy is what? If the initial is 0, then W minus 0 is F dot dx by work energy theorem, and dx is the displacement, right? So dw dx is nothing but force, and if we put a minus sign, because you know that this is always in a direction such that it tries to oppose them. So that is the general nature, in general principle of nature, that it tries to oppose its cause always. So the force will act in a direction such that you can just oppose that actual cause of generating that force, which came from the energy stored, right? So it tries to oppose that. So that is a negative sign, but the absolute value is just the rate of change of work done. That is what is the force with respect to displacement for a given lambda, because W is dependent on both lambda and your I, and also dependent on X, as you see, because there is a motion. So this W, this energy is dependent on lambda I and X. So that's why dW dx for a given lambda will give you, with a minus sign, is the force, and the absolute form is dW dx. And the direction of force involved, which I told you, is generally denoted with a negative sign, because it acts in a direction to decrease the actual source cause, which was the magnetic field for a given flux, right? And the co-energy is like this area, which is the converse of that. So it tries to aid it, right? So both are actually trying to tell the converse of it, because you know that if you take just reverse the two terms, then it will be obviously changing the signs, right? But you understand that this is the energy we are interested in. This is the energy, right? And we can quantify the energy as total energy as half into B into H. But please remember, this is energy density, right? Per unit volume. So what will be the unit? Unit will be joules per meter cube. In SI unit, I am telling. So it's joules per meter. Also, you can write it as half into what I told you, B into what is B? It is mu H. So you can write H as B by mu, and people use in this form also, B square by 2 mu, and you can use B square by 2 mu 0 mu 1. Mu 0 is what? It is the air. It is the permeability of free space, right? Air. And then this is the relative permeability. So you can use for mu. So this is one form which you can use to quantify the energy, right? But please remember, this is energy density, right? So you can calculate actual energy as energy per unit volume was this. So total energy would have been the volume, whatever is the volume, you can multiply with it. But you also know that what is the force? Force is what is the energy? Energy is work done, del W, or del energy is work done. Work done is force into displacement. And just we can write in linear terms that what will be your force? Force will be, considering zero initial condition, force will be B square A by 2 mu 0 mu 1, right? So as you know, linear relationship. Otherwise, you need to differentiate. If the variation is not linear, you need to differentiate. Otherwise, this will be the value of force, right? What I am trying to tell you is quantifying or showing how to derive the expressions. See, you cannot directly divide if it is not linear. You have to differentiate. Hope you understand what I am telling. So that's why we did dw dx, right? Because if there is a linear relationship, we can directly divide. Otherwise, we have to differentiate the function, the energy function, with respect to displacement to get out the force, right? get the force value. So this is just the derivation using linear, assuming linear variation, right? So W is a linear function of X, linear function, assuming. So we can see in most of the equipments like in capacitor and some electrostatic media, if you use this formula, you will find that actually energy is changing linearly, right? That's why this formula works in many of the places. But first you need to verify whether the relation of energy with displacement or whatever you tell, that motion length actually, whatever length it traversed, that should be linearly varying with respect to the energy stored. Now that equation we will derive and we'll see if it is linear, then we can directly divide. Otherwise, we have to differentiate. That is the whole point, right? Because you know, if it is AX, if some form of work is AX, and you divide by X to get the force, then force is A. How you got it? You just did the differentiation, right? You do differentiation or you do division. If it is a linear relationship, then both ways you get the same result. Hope you understand what I'm trying to tell you, right? So there is an interesting thing that there is a variation. You know that there is a BH curve, right? So this curve, people call it BH curve, or I call it phi I curve. Because why? B is proportional to phi, H is proportional to I. Why? H is nothing but Ni by L. This is coming by Ampere's law. So as you know, H is proportional to I, and B is what? Phi by A. So if once it is designed, once the system or the magnetic circuit is designed, once designed, I can write B proportional to phi and H proportional to I, because neither the length nor the cross-sectional area will change because the material or the system is designed, right? So I can write this as phi versus I or B versus H. And due to saturation, you know that why saturation happens for any ferromagnetic or any magnetic material is that there are dipoles. There is nothing called as north and south that we name. So what is north and south? Where the flux starts emanating, we call that north pole, and the flux lines come like this and goes inside the magnet like this, because of the small dipoles, right, inside the material. Now once all the dipoles are aligned with the external field, then you get the maximum due to the current flowing through that, due to the current generating the flux and trying to align all the dipoles in its own direction. Then all, with the increasing value of current, increasing amount of force to align the dipoles, one time will come all the dipoles are aligned, and when all the dipoles are aligned, maximum maximum flux you will get. Above that, if you pass more current to get more flux, that cannot be happening, right? And that increment is very small. So as you can understand, this slope, what it gives you? It gives you mu, as I already told you. Now you see, mu is not constant. Mu is the slope of this curve. Now for the same magnetic material, which was initially behaving to be a very good magnetic material because its slope was high, mu was high. But here, once saturated, it behaves like a simple air gap because mu is very low, or I can call it slope is almost zero. So it is very low, and then it is behaving like air gap, right? Or close to air gap. That's why we say that with saturation of a magnetic material, what happens? Your permeability also reduces. And once the permeability reduces, what is the formula for permeance? Mu A by L. And what is the value of inductance? It is N square times permeance, or N square by reluctance, which is nothing but N square mu A by L. How we derived it? It is nothing but N phi equal to Li. N phi equal to Li, why? Because that's how we derived the inductance, right? That's how we defined inductance. that it is nothing but the quantity which actually is a proportionality constant, because we know that lambda proportional to I, and that proportionality constant is actually nothing but inductance, self-inductance. So we got it like that, and from here you can just plug in the values and get the relation. So you see, if you wound some coil over a magnetic material and try to pass some currents, and once you cross some thresholds, slowly once it starts saturating this core, then your inductance offered will also change with the changing value of current. Please try to understand that. So this n phi equal to Li, although it looks like a linear relationship, it is not true, because phi versus I is not linear. And not only phi versus I is not linear, but the inductance variation with respect to current is also not linear, because phi versus I is also non-linear. So with current, you go to saturation zone for a magnetic material, and with that your inductance value also decreases, because mu decreases with increasing current values. Hope you understand what I am telling. Up to this it is clear? Yes, yes. Like but there is a difference. There is a very good difference. In dipole, how the field looks like, plus to minus, it is like this, but plus to minus inside it is like this. But if it is a north pole and a south pole, which does not have any practical significance, we only term it like that. If you cut the magnet, this is also north-south internally. There are dipoles, kind of dipoles. But you know what is the difference? If you flux is emanating like this, up to this it looks like same. But inside the magnet also, how is the field line? It is from south to north. Unlike the electric dipoles. Electric dipoles always from plus to minus. But in the magnetic dipoles, we term it like that. Flux is outside the magnet, it is, or outside the dipole, it is N to S. But inside, it is just from S to N. So there is a difference. Okay. So that's why you tell that divergence of B is 0. Because any closed surface you enclose, it will cross. It will cut it, and then again it will cut that surface by Gauss law, but again influx will be there, because magnetic monopoles cannot exist separately. Hope you understand. But electric monopoles or electric poles like plus and minus can exist separately. That's why the divergence of the electric field is not 0, but the divergence of the magnetic field is always 0. Always 0. So there is a fundamental difference. Yes. And you must check the data sheets or the application notes of some course like Woods or some other material or other company which makes inductor, which makes actual, or Delta. You can just check their application notes. You can see the workable range of currents. After that, obviously, that coil will burn out, but before that, your core enters into saturation. And once your core enters into saturation, what will happen? The inductance offered by that system or the material which is designed for the use to give a particular inductance value also changes. So for inductors, you see the application notes. Frequency is also very important for which you design that material. And that's why we say that with increasing frequency, the inductance or the size of the inductor reduces. That is also a perspective. And for a given frequency also, your current variation will change the saturation level, which will completely change the magnetic characteristics of that core, in turn, which also practically affects your inductance value. So things are not very, how it looks in the relations, in the formulas, they are not that trivial, right? Because there exists saturation. So that it does not exist saturation, or so that it does not enter saturation in a way, what I can do? I can introduce purposefully a small air gap so that the inductor value does not change very rapidly with slight change in currents. Because what you know, so that is our discussion for the next slide, I think. So I can tell here also. So why you introduce air gaps? Can anyone tell me? To design inductors, you introduce air gaps. But for transformers, we don't introduce air gaps. We don't actually want air gaps. What is the purpose of introducing air gaps? You understood the problem, right? What is the problem? Now, why the solution is to introduce air gaps? What you told, I did not get. Just please unmute and speak. I cannot understand what you are writing. SATN means I don't get. SATN reduce means? Oh, saturation. Okay, okay. You are telling that saturation reduces correctly for the same value of MMF. Correct, that your saturation can never, it can never go to saturation. Correct. And obviously you use inductor in series. That's why it has to bear the same amount of current. And obviously with air gap, what you are doing is actually electrically you are not doing anything, but magnetically you are reducing the chance of that flux actually saturating the core, because now your reluctance increases. So it can not, for that particular MMF, your inductor core will not enter into saturation. For the same MMF, now the reluctance is more. That is the whole purpose. But with that, I got, there is a slight, I can say there is a slight disadvantage. Can you tell me why? What? By introducing air gap, okay, you reduced. So I can write, by introducing air gap, one thing you did good, for same MMF, your phi is low as reluctance of core increased. Right. So saturation avoided. For a large value of current also you can avoid saturation. Obviously the coils should also electrically assist the pass of that current. But I'm thinking that okay, you used correct SWG wires and cross section areas are okay to pass that amount of current. So for high amount of current also your flux is low. For same MMF, due to the increased reluctance of the core by introducing air gap, you have now increased your band of saturation because your flux reduced. But what disadvantage you got out of it? Can anyone can you tell me? There is a small disadvantage with the inductance value now. Initially, inductance was what? N square times permeance, right? Permeance was very high initially, but what was the disadvantage? That it was varying rapidly because the saturation characteristics was like that. It was entering into saturation, right? Because the low reluctance of the core, the flux was high, and for even a small increase in current, you enter into saturation. That was the problem, for which your inductance value was rapidly varying and decreasing. But now a new problem came that since you introduced air gaps and the core reluctance increased, your inductance value became low. Now the problem is different. Now the problem is that your inductance value is low, but your inductance variation with current is very less, and you also avoided saturation. So please keep these things into your mind, right? And accordingly you can solve the problems. And also one point, that for the same flux, you now see you have the reluctances of the air gap and the reluctance of the core. For the same flux, you have two paths now, like the electrical circuit of representation of the magnetic circuit. Now maximum MMF drop will happen across what element? For a given flux rotating through the core, which has two parts, the air gap part which has a higher reluctance and the core part. Core part is also dimensional wise it is large, but the reluctance is very small because it is 1000 or 10,000 times more, right, of the air gap, because your mu r of iron is around 10,000, right? So this is 10,000 times approximately more. So for the given MMF, you have some fixed flux rotating inside the magnetic circuit. Now tell me, across which part of your this of the two parts, that is the air gap and the core, is storing the more of the energy? Air gap is storing more energy or core is storing more energy? Magnetic energy, I am telling. That you can see from the curve by the co-energy and all energy I told you, as well as you can see from here also. Which part, the larger resistance or the larger reluctance part or the smaller reluctance part, which across which element is the MMF drop happening more for a given flux? Obviously flux is rotating, series connection, right? So phi into reluctance of air gap or phi into reluctance of core, which one is more? Yes, air one is more, and this gives me MMF drop. Now once we get MMF drop across this one is more, can I tell the energy also? Yes, because what is MMF? What is energy? Energy is MMF times again your flux, because voltage into current into time energy. Similarly, voltage or MMF times current is nothing but flux. Magnetically, I am telling coherent terms. So you see phi square into RA is greater than phi square into R core. So you can see more energy stored by the air gap. Or what is the easy way to see? I told you B square by 2 mu is the energy stored. So if mu is more for magnetic materials, you see the energy stored is less. And if mu is large, like air gap, sorry, if mu is low in air gap, it is more. The energy stored or energy drop I cannot tell, because magnetic circuits don't itself consume any active power, but energy stored I can tell is more across the air in the air gap. So that's why we tell air gap stores more energy, right? So these are all the working formulas I have already explained to you. These are the working formulas, right? So B, how you define flux per unit area. Then I told you that work or energy is nothing but dF dx. Just the work energy theorem, and then the definition of energy or the definition of work. It is nothing but F dx. And what is force? dF dx with a minus sign. Sorry, dW dx with a minus sign. Just I explained some time before, right? And then I told you the formula of force, total force, and force per unit area is nothing but same B squared by 2 mu. And this is Newton per meter square, as you understand, right? This will be area will be coming down, right? Up to this, you are with me, right? So this is coming from half into B into H, which is nothing but energy per unit volume, and volume can be written as A into X. So half B H A X is nothing but energy, and energy is what? Change in energy. You are assuming zero initial condition is nothing but work done. So half B H A X, right? And H is what? Or I can write everything in terms of B. So half B square by mu Ax is nothing but, and mu 0 mu r you can write for a particular material. And this is nothing but the work, right? Or the energy. Because what is work? Work is nothing but change in energy. So assuming zero initial energy, you can just assume this is the energy, right? Stored. And you can just derive it with respect to X to get half B square by mu 0 mu r into A. And this is the force. And force per unit area, I told you B square by 2 mu 0 mu r. That is what it is written here, right? So force per unit area, you got the definition of formula, right? Similarly, you get the electric, for the electric field, if you use. So you know capacitor, half CV square is the energy stored. I told you, just derive it, dW dx. Now how can write? A epsilon naught by d, or x into v square. You derive it. You derive it and you will get that. So what is force? Force is, or force into X is nothing but energy. You can write in any forms, right? Whatever you want to actually derive. So see, just you derive, you will understand what I'm trying to tell. You can differentiate or you can just use this formula. So what is force coming? Half A epsilon naught V square by X square. You can also differentiate it. You got a minus sign. So mod of F is nothing but half A epsilon naught V square by D square. Now, if you want to check, you can cross check also by deriving the capacitor relation and then trying to derive it and see. So these are all the expressions we are getting, right? Similarly, you must know Lorentz force. How Lorentz force? How is Lorentz force defined? That for a current carrying conductor, what is the force experience? Or by the Biot-Savart's law, you must know what is the force being experienced. Everything you can derive for the magnetic field, and these are very fundamental equations which you must have gone through in the physics course, right? Then these are very practically used also. Like for example, EMF is BLV, right? Velocity. So these terms are all coming from these force equations, right? And you know that how they are derived, right? So they are all from the fundamental principles of physics, right? How your moving conductor actually generates a potential difference. All those relations. Similarly, you can see here how you derive everything. These are all induced EMF d phi by dt times the number of turns or the power. These are all some fundamental basic relations given for non-electrical candidates who don't have a non-electrical engineering background. They can just connect. If you have some mechanical background, you can connect how the electrical and mechanical fields are coupled and how to move from one to another, assuming a lossless energy transfer, right? Lossless energy conversion process you can assume, or how you can define the magnetic field, right? So this energy, I just told you how to define, okay? And magnetic from the density, you can move to the total energy, right? And this is the total energy stored, and the terms B, H all are defined, and this is the differential volume element, and you integrate and you get the energy density, right? So, and the total energy you get by multiplying with dV. And the energy density, if you want, is a half into B into H. I told you already. It is the energy per unit volume. So, joule per meter cube, right? So, now let's go to some problems, some easy example problems. So, the first problem I think is visible on your screen. Yes, so just try this problem once. So, I will give you some time. So, the magnetic flux density is given as 1.5 Tesla. So B value is given to be 1.5 Tesla, and the force density on the iron phase is being asked. So kindly try. Yes, done. That was easy, right? Can I know the answer? Any one of you, if have attempted? Just can write their answer. How you solved, you can just unmute and tell me. So discussion, I think, is more important than how you arrive to the answer. That is more important than the answer, right? So, any answers? If you have derived, you can just let me know. So they have just asked to calculate the force, and we have just derived that what is energy density half into B into H. I told you B can be written as H can be written as B by mu. So B square by 2 mu. It is nothing but your energy by per unit volume. So what is force density? This is energy density. So force is again force times yes. What will I write? Force into displacement is nothing but work done, and change in energy is work done. So this is B square by 2 mu. And this is energy, right? Total energy. So this side also should be total energy. And total energy is what? Area times X. So I cancel X from both sides. So what is my force per unit area, which I call as force density? It is again coming b square by 2 mu 0 mu r. So please note this is the formula, right? So you can just plug in the values and check. So what is force density? B square by 2 mu 0 mu r. What is B? 1.5 square by 2 into mu is what? Mu 0 value is what? Yes. But when it gets saturated, then your mu r will be 1 because it will simply behave like air gap. Understood? Mu will be behaving as mu 0 at saturation. So your it is 4 pi into 10 to the power minus 7, right? And Newton per meter square. So just check what it is coming. 0.89 mega Newton per meter square, right? Getting the same? Getting the same, right? Okay, let's move to the next problem. So there is a capacitor which is charged and you have some mass M connected. Obviously, it is hung over the negative plate and the dimensions are given as 20 centimeters square and the separation D is 5 millimeter. Please note the units. And the mass is M, which is unknown. And the del V, the potential difference is 5 kV for the capacitor, and it is asking us to calculate what is the energy stored in microjoules, and also to calculate the mass of the object that is being hung from the lower plate of the capacitor. So obviously, as you understand, what is the direction of force on the negative plate? The negative plate is being attracted, but the mass is also holding it in the other direction. By the free body diagram, you need to balance the forces. So F equal to mg, because this plate is stationary. There is no other mounting mechanism. The plate is this plate is held by some means. Obviously, they have to be maintained or separated. And other one is just hung freely by a mass. So it is not moving due to the mass being hung, right? So F equal to mg, and you can calculate what is the force. So use your basic principles and try to calculate. So I'll give you 1 minute, right? And then we'll jump into DC machines. So try. Try using the relations and energy expressions. We have already given you A and D values. And you can use that epsilon naught, which is nothing but permittivity of free space, because this is electrostatic, right? And what is its value in SI? It is 8.85 into 10 to the power minus 12 farad per meter. This is electrostatic, right? Previous one was electromagnetic. This is electrostatic. I told you, use the energy, right? And then what you can write? Half A epsilon naught by D into V square. That is the energy. Now what is energy? F into X or F into D. Force into D, right? That was easy. Why you cannot do that? So what was force? Half A epsilon naught V square by D square. Now use this, equate it to mg. Now we know anything more? Yes, we can calculate the force, right? half times 20 into 10 to the power minus 4 because centimeter times 8.85 into 10 to the power minus 12 times V. What is V? 5 into 10 to the power 3 because kV whole square divided by D square. D is 5 millimeter. So 10 to the power minus 3 whole square. So you got the force, right? So energy stored you calculate half CV square, half A epsilon naught by square by D. And what is M? Small m. Small m into G is nothing but this. What is G? G is 9.81. Right? It is acceleration, right? So this is nothing but force by mass. Or you can write meter per second. Now divide it by 9.81, you get M. Now what is it coming? So G is nothing but, so M is nothing but times 9.81, right? You do it and tell me what is M coming. Tell me in kg because it will give you in kg. So we have more topics to cover. So I am writing the answer for you. You can just check. 9.02 into 10 to the power minus 6 kg. So you can use 9.81 as the G value. Okay. So MKS system SI units you do and you find M as this. And the total energy stored I am also giving you. By this you put in every values and you get energy stored. I am giving you the value. Energy stored we are getting as so it is coming 44.25 microjoules, right? Just check. Okay. So this is one and this is another. So both you can just plug in the value and just can balance the forces. So balance free body diagram, right? Then you can get. So hope you understood, right? Any doubt you can just ask me in the concept, right? Any doubt? Yes, any doubt? Hello? Okay. So we go ahead with the DC machine. So we go directly into the DC machine construction and working, how a DC machine is working, right? So any idea if you have must have learned some from electrical engineering background, must have gone through DC machine. So it is simply a machine where you have excited, you do the electromechanical energy conversion, you have some electrical voltage applied in some coils which results in the flow of some current, and the current carrying conductor is actually, if you provide electrical energy there will be current in the coils and there is a magnetic field and you generate some EMF. So you have externally connected with some commutator arrangement. There is a commutator arrangement. So there is a ring which is cut like this and this is known as a commutator, right? And there are brushes. So what it does, brushes are stationary, right? Only ring moves and brushes are placed at GNA. GNA is nothing, don't get afraid, it is a point where the flux is zero. So flux, if we start from theta, how will the flux look? Here there is no flux. So flux starts like this and ends like this, right? Because from one point flux is getting generated, another point it is entering. So I drew it in the opposite. But as you understand, once you approach the pole of the DC machine is like flat top, right? So the once you approach the arc, it is almost constant, the flux density. Then it reduces again as you move away. And as you go again to the south, it is the other direction. And it goes up. So like flat top, right? And you apply some kind of voltages for a motor. Assume it is a motor. So you have to apply some voltage. Some voltage means some current will flow. Some current flows through a magnetic field. What will happen? It will generate a force, ILB. This side will generate a force in this direction. This side will generate a force in this direction. Okay. So force, right? So ILB. So you just use your right hand, right? So you place your finger and then you try to curl. Sorry, it will be in other direction because IL cross B, the force on this conductor is coming opposite, right? This side. You can also use your left hand and right hand, all those things, but I try to do it by cross product, right? So just let me remove this part. And magnetic field lines are always from north to south, as I told you. So generally that rotation will be in this direction. Now, as you understand, current in this path is like this, but only up to the point that this conductor rotates and comes to this direction. Then again this conductor will be flipping the current, because after a rotation this conductor will come this side, right? And the current will have to change. Why change? Then if it does not change, that is, if this process is not flipping, then the torque smoothing will not happen. So in order to get a smooth torque, because once this comes in this direction and the potential does not change, then it will be just steady, right? It will not get the rotation, continuous rotation. The current also needs to be changed. So that mechanism is done by the commutator, right? Commutator does what? Commutator flips the polarity of the, or you can call it as a mechanical rectifier. Because what will happen? What kind of voltage you will get? Your voltage will be nothing but EMF is nothing but BLV. EMF across the port, this port. So this coil, when rotated in the other direction, will generate opposite polarity EMF. Now, if you connect some load with it, this will also see the opposite polarity EMF, which we don't want. We want DC, right? And if it is a motor, then we want the torque also to be smoothened. But assume that it is acting now as a generator. You now rotate it. Then the polarity of EMF will actually be like this, because E is nothing but BLV. So E is also like this. But this is not DC. And it should be not DC. Because if the coil is rotating like this, then the flux also is like this in the other half. So the polarity reverses, right? The polarity impressed across the same point is reversing in a half cycle. So the load sees a voltage like this. So the load not like this, you need to flip the polarity or flip the conductor after a half cycle rotation. That task is done by the split ring. You also rotate it, and then the brushes are sitting like this. Brushes are fixed, right? So once the split ring flips, what happens? The other conductor now comes into action with comes into contact with the first brush. So then it is not happening that the current also, because now the current is passing through the second conductor in the same direction as that of the first conductor after a half cycle rotation. So that is a kind of mechanical rectification, right? Mechanical rectification by commutator, which we place the brushes so that the transfer of the movement or the mechanical rectification by the commutator can happen without any spark. So at that point there is no voltage induced. So that is the way how you do it. So if it is behaving like a motor, I am talking about the back EMF, and the back EMF induced should be be zero when the flux density is zero. And when it is behaving like a generator, I am talking about the EMF being induced by the generator. Okay. For a half cycle rotation. So there you don't force with any voltage. And when you are changing the position of the brushes, the external voltage is also there, but it is not in contact. Please try to understand, right? So the EMF, the internal EMF plays a significant role the, for deciding the location where you are actually placing the brushes. Okay. So with this, I can say that this is a basic working principle that you have some current carrying conductor in a field, in a magnetic field, you get some torque, you get the rotation. But if it is a generator, you please understand the current direction reverses because it is now delivering current. Previously, the motor was taking current, so current was in this direction, but it is behaving like a generator. That's why we use left and right hand for two different things to get the EMF induced and to get the motion. So if it is acting like a generator, you don't apply any voltages. You get voltage, but you have to rotate it. If the rotating conductor is cutting the magnetic field, then EMF is induced. And the induced EMF, the current and the induced EMF always tries to oppose the flux. So that is what you call armature reaction. By the nature's law, any action tries to oppose its source cause in the similar dimension. So this current also tries to oppose the main flux, and that is what you call armature reaction. It always tries to decrease the net flux. So that is what you simply call as armature reaction. But please understand that for same polarity of voltages applied to a motor and a generator, the rotation will be in the different direction because the current direction changes. So torque is proportional to phi into I. For same polarity voltages, you see the flux is in the same direction, but the current flips for generator and motor. So for DC machine, this is a special thing that DC machine, generator and motor rotate in different direction for same polarity of voltage. Same polarity of voltage means the terminal voltage, the terminal at which the machine is, we are tapping out the voltages. For a motor, if I give plus 250 volts, and for generator also, if I get out the same ports and I label it as plus and minus, and I try to take 250 volts from the generator, please understand that it means I have to rotate the generator in a different direction than I did at the motor. So if this is the terminal and you want to apply here plus minus 250 volts for a motor and you saw that the motor rotated anti-clockwise, then if you want to take positive terminal out of this and negative, you want positive voltage to appear at this coil at this side and negative at this, then you have to rotate in a different direction. Assuming that the commutator is already connected, I am telling about the brush, right? Say this brush is plus, this brush is minus, you assume, and you want the polarity to be like that only, then you have to rotate the conductor in a different opposite direction. Because please understand the generator current and motor current are in opposite direction. Agreed that inside the armature coils, in a DC machine, armature coils are in the rotor itself. And the current is flipping its direction in half cycle because the B is changing. The B, I told you, na ILB, the B is reversing from N to S. So the current is alternating in nature, but there is the commutator. That's why you don't see the alternating current. But I am not talking about that current which is inside the conductor. In DC machine, when we draw DC machine, this current, the armature current, is current outside the conductor. That current is not flipping outside the commutator. That current is DC in nature, but inside the commutator, once you go into the coil, in a half cycle, the current direction flips because the B flips. Get my point, or I need to repeat? So all the analysis we will do now are of the voltage and current that are tapped outside the brushes and tapped outside the commutator. They are DC parameters. Is my point clear or not? Because inside the conductor, the current is not DC. Because in a half cycle rotation, the current will flip its direction, right? There is two conductor, right? So you need to understand in a coil how the current is actually circulating. So you connect the conductors in series fashion for the voltage to aid actually. You don't want the voltages to cancel, right? Do you want the voltages to cancel? So if the voltage is plus 5 volts, like a battery, got my point? And the voltage in this conductor is also plus 5 volts, and you connect both. Then what is the voltage you get across the terminal for a generator? 0 volt. Do you want it? No. That's why I placed one conductor near the N pole and one conductor near the S pole. Then if you connect some battery and try to flow a current for a motor, the current can flow like this. Or if you want to do it as a generator, please understand, if you want to operate it as a generator and generate some voltage, your voltages will be of opposite polarity, like plus minus for this conductor and minus plus for this conductor. Why you know? Because your volt velocity of this conductor is like upwards and velocity of this is like downwards. You have a coil, one coil trying to go up and it is mechanically connected, then the other coil is coming down. So the velocity of the this side coil is downwards. Try to do BL cross V in order to check the EMF direction. You will find EMF also reversed, current also reversed. Then everything is like reversed. Then you can connect the two coils in series to get the double the voltage of one conductor, double the EMF generated in one conductor, tapped across the 2 points. But why I again place the commutator is due to the reason that I don't want a AC voltage being appearing that is toggling in a half a cycle. That is not AC. That is, we don't want AC to impress across the load. My load should not feel that the current is toggling in half a cycle or the voltage generated is toggling in half a cycle in plus and minus. So I just flip. Along with the conductor, I flip it, right? So the load will never see the flipping, right? Because I also flip the connections. So to the load, it is still positive. Wherever it was positive, load positive terminal still gets positive conductor. Whichever conductor, the other conductor came here and gave the positive supply to the positive of the load. So the load feels it is still DC, right? Brushes still sees one polarity. At buses are fixed, right? One brush sees one polarity. But the current conductor inside the machine sees two different directions in one cycle rotation. Do you get my point or no? Because the EMF is also flipping, right? Yes. The EMF is also flipping because of the velocities. If you see as a generator, due to the velocity difference, one up, one down, the EMF is opposite. And that is why the current is also opposite, right? One going like this and one coming like this. This is how it is designed. So that was the concept that how DC machines actually work by the basic laws of physics. And you can reduce the ripple by introducing more conductors throughout the periphery of the armature, right? So as to smoothen the overall voltage quality, right? And to get a more pure DC, right? And then DC machines. Now coming to the DC machines, you have the motor and generators. The motors, generators can both be classified into a unique or in a similar category, like based on the nature of their excitations, how they are excited. So as you can understand, to produce torque, we'll need two things. We need armature conductor as well as field, because the field will generate the flux, the armature will carry the power. We call it a coupling circuit and a power carrying circuit. The power carrying circuit is the armature circuit, which has the conductors through which the power is exchanged from mechanical to energy to electrical, and from electrical to mechanical. So that is the role of the armature conductors. But there should be some flux creating fields. So those conductors are termed as the field current conductors. So both conductors or coils or conductors. Two conductors make a coil, but as you can understand, the power is handled by the armature part, and the field is happening to generate the flux. Why you need flux? Because without flux, you cannot have the cutting of flux or the relative velocity, either in the from mechanical to electrical or electrical to mechanical, but you need some changing flux to generate some voltage by the law of physics. So flux cutting is necessary through relative motion, because here nothing is varying with time. Because if you have a current flowing through a coil, that field is not changing with time, but the conductor is cutting it, so it sees a different flux every time. So cutting the flux and generating the voltage, right? That's why we rotate the conductors in the armature, so that there is a relative motion. And if there is a relative motion, even for a fixed flux, if there is a relative motion of the conductor, the voltage is generated. That is how the voltage is electrically it is generated, by the motion of the conductor. Or in other words, by giving a voltage, I can generate the motion by generating the force, right? I told you for the generator that it is how we do it. But based how the excitation or how the flux creating media will be designed, that actually declares the type of DC machine design. So may it be separately excited, so the field coil is sitting separately, right? So this is the field coil, and this is the armature, right? So the armature total conductor resistance, lumped resistance, I can model like this, and this is the port available to you after brushes. And this is the field, this is the armature, right? They are separate, right? So that is why we call it separately excited. Now self-excited, how it will look like? This is the rotor where the armature is there, and we keep the field coil also. Field coil is generally of larger resistance for a shunt. Shunt means the field coil is parallel to the armature. So for a motor, you give the voltage, and obviously the field needs to be having a larger resistance, because the field current should be small in order to create a sufficient flux. But the voltage is larger, right? DC voltage. So that's why the resistance should be larger compared to that of the armature, because the armature needs to have a smaller resistance for the power to flow. For the motor, it actually takes the current, right? And the energy conversion happens, this voltage, which we call the back EMF, times the armature current, should be equal to the mechanical, right? It is the energy or power getting converted after the losses. So loss is the drops in the brushes and the conduction losses, that is the RA and RF. Those are all the losses. But after that, however, is the how much ever power is remaining, that is completely converted to mechanical, considering there is no mechanical losses. So EB into IA is electrical, and T into omega is mechanical. Obviously, there are losses. So as you can understand, lossless energy conversion, which we can use in some problems if they specify to neglect mechanical losses, right? From the electrical side, we can use this formula. Coming from the electrical side, only we can account for the armature drop and brush drop, armature resistance drop and brush drop. These are all the problems we'll discuss, and you will be able to understand. So there are, after you understand that there are shunt and series and compound. Compound is nothing but mix of shunt and series. So there is the shunt. Shunt means parallel field, and also there is another coil sitting here in series, and that forms the compound. Both combination of series plus shunt field. And the compound is also two types, the cumulative and differential. and the shunt and series I told you, right? And they may be separately or self, right? So now coming to the characteristics of the generator of different kinds of DC machine and the characteristics for the motors for different kinds of DC machines. So I will just write the equation. So for generator, as you understand, we may take a series generator. And as you understand that for series generator, the flux is proportional to. So how the series generator looks like? You have some armature resistance, and since it generates some voltage, I will leave it like this. There the voltage will come, terminal voltage, where you can connect the load, and then you have the coil, series coil, RAC. Please note RAC, and for shunt you have, this is the armature resistance. Shunt is like this. Please note one thing. This is also the terminal. You get VT out of it. So this is shunt generator. This is the field resistance. Please note the series field resistance must be less than the shunt field resistance. This is because the series field has to also pass the load current, and shunt field needs to be higher because it has to withstand large voltage or large terminal voltage. So you get my point that this, as per design, the series field coil resistance of a series generator is generally lower. The resistance is generally lower than that of the shunt field coil, right? And as you also understand, this flux is proportional to load current. If I consider load or armature current, right, both are same. There we don't consider, no saturation is considered here, or no armature reaction, because what you understand that if current increases, this also introduces the armature flux. This increases, and armature flux opposes main flux. So if IL is too high, phi net reduces, right? Okay. So as you understand, the voltage is increasing, but up to a certain point, due to saturation and armature reaction, the voltage is limited actually, or it is not increasing that much that it used to previously. So due to saturation, the flux saturates, and then further if I increase the field, then it will not boost the voltage. So how it started is that I had a residual flux in the generator, and that created small amount of voltage once I started rotating. That voltage led to some field current, which further increased the net flux, and it boosted the voltage. Then this voltage further increased the flux, because if V increases, I am talking in no load, right? So this V, there is no current IA, so complete current is flowing to generate the field and then the voltage, right? So this voltage is building up, but please understand there is a critical speed. So N should be greater than N critical, and there this slope is defining the field resistance RF. This field resistance should also be lesser than a critical field resistance. Only then the voltage buildup is possible as per the intersection of the line, resistance line, and the characteristic curve. So these two conditions should be maintained, should be satisfied for voltage build-up, right? So now you understand the series and shunt generators, because the shunt generator flux, ideally phi shunt does not vary with IL, but practically as load current increases due to armature reaction, phi slightly reduces, not much, right? So since phi shunt is almost constant, then you get best possible I can say flux being maintained for shunt machines. Right. So if I draw for compound also, for compound, series and shunt, the external characteristics, that means the load characteristics, right? The voltage and current. So what I desire is my full load, at my full load, my voltage should be ideally rated, right? Or ideally the no load voltage should be ideally the rated voltage. That is the desire, right? But as you know, with load it will drop, right? For series, you know that at zero voltage, at zero load current, there is no voltage induced there because the field is also zero. But with field, I can get slightly increasing voltages, right? Like this. For shunt, you can see what is the Vt minus IARA is nothing but EB. So how you write the equation is like this. This is the voltage Vt, and here you have the shunt field resistance, and this is EB, right? Now for generator, the current is outwards. So what I can write, EB minus IARA, sorry, EB minus IARA it will be for generator. This is the induced voltage, right? Induced or generated voltage. Minus IARA equal to Vt for generator. IA or IL, because IF is very small, right? So what is, you can write, this is IA, this is IF. IF is going into the field, and this is the current, net current, IL. So what I can write, IA equal to IF plus IL. So what you can see is that if I write like this, EB is proportional to, so VT let us take, so VT equal to EB minus IARA. So as you see, VT and IA are related like this. So as you increase the load current, what will happen? As you increase the load current, for a given, let us say for a given speed and given flux, if you try to increase the load current, your voltage will decrease, right? So as IL increases, VT reduces. But you need to understand, for a shunt machine, if VT reduces, field also reduces. So the reduction is steeper. Or you can say reduction is due to 3 points or 3 causes. That since your voltage is reducing, your flux is also reducing, and your drop is also increasing. That is also reducing VT, and your armature reaction is also increasing because the increased load current is also trying to reduce your flux due to the armature reaction. So this steep decrease, right? But if you have a separately excited machine, your steep decrease will not be that much like the shunt. So this is, or I can write using a different color. This is for the separately. And this is for the, ideally it should be increasing, but as you understand that after some time it will reduce, right? As I already told you, ideally a series DC generator, if IL is too high, then voltage reduces due to armature reaction. Got my point, right? It will not increase up to infinity. Up to some time the voltage will increase. Then what will happen? It will steeply reduce because that armature reaction will start playing a role, and the voltage will slowly start to reduce. And then you have few other curves like the level compound, over compound, so level compound means that at no load and full load the voltages are same, terminal voltages. So that is how you turn level compound. And that is the over compound. And you have the under compound, right? The under compound is still better compared to the separately excited because of the series coil, additional flux you get. So separately excited shunt has only one source of flux, and your under compound is still additive in nature. It has series and shunt both. So there is flux, and since there is more flux, you can understand that the decrement with increase in load current is slower. So that is how under compound, right? So this was of the generators, and coming to the motors, I will only do for series and shunt, right? The characteristics. So there are 3 characteristics. Remaining 3 are for the shunt, right? And you will understand. If you understand these 2, then you can easily understand for the cumulatively compound, right, machines. Up to this you are with me, right? Okay. Then for the DC series motor, let us see. What you know? For DC series motor, your back EMF. So motor you have applied constant voltage, right? Motor also you have the armature with a small armature resistance, but the voltage applied is constant. Now for series motor you have a small field coil also and the armature. For shunt, what you have? You still have the rotor and armature resistance, but please understand it is having a shunt field coil with a larger resistance. But one more thing is that motor takes the current, unlike the generator which delivers the current. Similarly, motor takes the current. Always the line is having current like from source to the motor terminal. So current is like this. What you can write? If this is back EMF, you have to write like this, that Vt minus IARA, because this current is IA, this current is IF. So Vt minus IARA is nothing but EB, but your current line current is nothing but IA plus IF, where your IF is nothing but Vt by RF. And for series, what you can write is IA is nothing but line current, both are same, and your field current is also nothing but IA equal to IF, line current, right? And your EB is nothing but Vt minus IA RA plus R series, right? The equations like this. Understood? So what is EA? EA is K times phi omega. What is omega? Omega is EA by K phi. What is EA or EB? V minus IARA by K phi. So as you see, if I try to draw omega versus I, for a series, what will happen? V by K phi, but phi is proportional to I, so I write I minus I get cancelled, RA by K. So likewise, I have a hyperbolic relationship. But as you understand that at high currents, I told you high currents, phi not proportional to I, so phi becomes constant due to saturation and armature reaction. So then what happens? Then you get what kind of relationship? A linear relationship due to armature reaction. But that is at a very high current. Similarly, if you try to determine the torque versus speed characteristics, then torque is nothing but K phi Ia, and it will understand it is proportional to Ia squared, since phi proportional to I for low I. But as you understand, at high I, flux is constant, so it is linear. Torque is proportional to I at high currents. So how will it look like? Torque versus speed characteristics. First it will look like, torque versus current characteristics will look like this, like a parabola, and then it will be linear. So likewise you build the characteristic curves, right? Similarly for shunt, what is your EMF? K phi into omega. So omega is what? V minus IARA by K phi. As you understand, it will be reducing as the IA is increasing. So ideally I told you that as IA increases, it is a linear relationship, right? So omega reduces. But I also told you that as IA increases, your phi also reduces slightly due to armature reaction. So now your IA increased, omega reduced, okay. You get my point? Till you did not consider anything, it was a straight line with a negative slope. Agreed. But also you take into consideration as your IA is increasing, your phi is also trying to slightly reduce. Why? Because of armature reaction. Because that main flux created by the field is now opposed by the currents which is flowing through the armature conductor due to the armature reaction, and it is trying to reduce the main flux, which in turn is reducing this k phi denominator, which is slightly trying to increase the speed. So if this is without considering armature reaction, then this is with considering armature reaction. Slightly upward, the slope slightly became less steep. Hope you get my point. And then similarly, what is your torque versus IA? To derive the torque expression. So torque is equal to k phi into IA. And here your flux is almost constant. But as you understand, phi reduces as IA increases. So it became this, like this, with armature reaction. This is without armature reaction. So likewise, you can develop the curves. Okay, so now I will jump into some practical problems. I will take 5 more minutes and I will finish most of the problems. The first problem says that I have a DC shunt motor. So let me just draw the DC shunt motor. And I have the large resistance field coil. I'll take 5 more minutes, okay, to solve maybe 3 or 4 more problems. Now it is asking you terminal voltage Vt equal to 1. I think there is no problem, right? If I take 5 more minutes, there are 3-4 problems, and then I can wrap up. Any problem? Yes, sure. Then I can take more, right? So 1 per unit. So voltage is 1 per unit and speed you consider as 1 per unit. Means rated. Then armature current is also you consider 1 per unit. Then it is asking suddenly voltage became 0.5. And they are asking you to consider resistance, armature resistance to be almost 0. Here it is mentioned, right? Negligible armature resistance and constant power load. Constant power load means what? The motor shaft is driving a constant power load. Now I told you in lossless energy conversion, torque into omega is nothing but EB into IA, back EMF into IA. Now you see, initially IA was 1 per unit rated. VT was also rated. What was your EB? EB was equal to VT because RA is almost 0. Throughout the problem, you can assume VT and EB to be same because they are mentioning negligible armature resistance. Then what is initially EB? Torque into omega or EB into IA is constant for constant power load. Now you have seen that this is the case. Voltage is 0.5 per unit now. So what is the new EB? EB new is also 0.5 per unit. Now what will be IA? Initially EB1 into IA1 should be equal to EB2 into IA2. EB1 is 1 per unit, IA1 is 1 per unit initially. But since the load is constant power, once EB2 is 0.5, as given in the problem, VT equal to EB because RA is almost 0. And what is the new current? New current is IA per unit is also 1. So IA2 is 1 by 0.5 or 2 per unit. And what happened to the speed? Speed EB proportional to phi into N or omega, whatever you tell. Now EB became 0.5. Now flux is still kept at 1 per unit. So EB became half, speed also became half since flux is constant. So speed is 0.5 and IA is 2 per unit. Option A is the correct answer. So in these problems you try to actually write the formulas and check what term are varying and what is maintained constant. So got the problem? Got the answer? Why it is like that? Or I need to re-explain? Kindly tell me. Please let me know if you need any explanation. Or I will proceed, right? No, it is not asking you to consider armature reaction. Why? Because see, armature reaction is significant, but the field is too strong. Okay. So I told you na, that much significant difference is not taken into consideration. In most of the problems in DC machine, you don't, while solving, you don't take into consideration the armature reaction. I told you for knowledge purpose that how the curves will, in real world, how the curves will slightly deviate from the ideal curves. But in books, you can see ideal they are drawing. Like they are assuming phi proportional to IA square, sorry, torque proportional to IA square. But that is not practical because flux will be limited due to saturation as well as armature reaction with increasing IA. So that is not true completely. Up to a point it will be parabolic for a series, the torque with increasing current, then it will be flat, varying linearly with current because flux will be saturating, right? And obviously there will be some armature reaction also. So the flux will tend to reduce or maintain or stay at a constant point. So those things, armature reaction, while solving problem is nothing is significantly mentioned that okay, due to armature reaction the flux is reduced, like for example 0.7, the flux becomes 70%. Then you can assume in the new case. But in the old case and the new case, if nothing is mentioned, then the flux can be assumed to be constant, right? Because it is a shunt machine and you are impressing constant voltage across the terminals of the machine. Then for a constant voltage, if armature reaction is neglected, then for a field resistance, for a constant voltage, if armature reaction is neglected, your flux is still constant, right? So that is the significant flux that is created from the field coil, right? That's why we are assuming the flux to be maintained constant. So you can ask me the question that how the flux can be maintained constant. It is very easy. You can just change the armature field, the field resistance. Voltage became 0.5. You can change the field resistance and maintain flux to be constant. Those things can be done, right? Clear? I can move to the next problem, right? Okay. Per unit means that it is rated. Everything in per unit means everything is rated. The base is rated. So voltage 1 per unit means rated voltage. Current 1 per unit means rated current. Speed 1 per unit means rated speed. It is a form of representation to quantify the changes. That is 50% of the rated means 0.5 per unit. It is a form of representation, right? Clear? 2 times means 2 per unit. Per unit representation, this is called. With respect to the base, which is the rated, I try to parameterize everything in terms of the base parameter, right? Base parameter of the voltage, which is rated, base parameter of the speed, which is rated speed, like that. Understood? Yes. So it is asking you to calculate the full load speed, right? For the 4-pole 20 volt 24 horsepower shunt motor having the following data and field current is given, armature resistance is given, flux and number of armature conductors, so everything is given. So similar approach, only the parameter is now different parameter it is asking. So you apply E equal to phi z n full load P by 60A. For wave connection, you know, P or number of parallel path is 2, right? And number of pole is 4. So you plug in every values, and NFL you can write as 162.4 into 60 into 2 divided by flux per pole is given milliwebers, right? 40, 160 is the EMF, number of armature conductor, sorry, and then 4 is the number of poles. Then your NFL in RPM becomes 761.25 RPM. So this is how you derive, right? That they are asking you to calculate the or match the characteristics, right? So matching the characteristics, I told you that for torque versus IA, ideally speaking, your series should be like a parabolic series, because torque is proportional to phi IA and phi is proportional to IA. So torque is proportional to IA square. So it should be parabolic, and your shunt should be a linear characteristic because flux is constant. So torque proportional to IA, right, for shunt, and this is for series, right? So it is now clear that for 3 you need to go with shunt, which is A, and for 2 you need to go with series, which is B. Now there is another much steeper curve. This curve will be of the cumulative compound because it has both series and shunt. So much steeper rise, right? So 1 goes with C, and D is the least, the flux, which is decreasing actually because it is differential compound. So the final one, 4, goes with D. So I think this is matching. Yes, A is the correct option. Thank you. So there are 2 more problems. So here they have asked you to calculate when the generator is just running as a motor. So with the generator, you first try to derive the back EMF, and then steps I will write. Try to derive back EMF of generator and motor separately. And then you know what? That flux back EMF proportional to phi times N. Flux is constant, right? So you can do EB1 by EB2 as N1 by N2, and this is the thing you need. So I already told you that for generator, you have to apply the voltage. You have to take the voltage from here. This is the field. So EB minus IA RA equal to VT, and for motor, VT minus IA RA is AB. So once you try to find out, because VT for generator is given, similarly VT for motor is given, and the speed is also given. So you try to determine the back EMFs. The speed of the generator is given, so EB1 and N1 are given, and EB2 can be determined because the power and voltages are given, and the shunt field resistance you know. From there you can determine the EB of motor. EB of generator can be directly found out, and the flux is constant, right? Because it is a shunt machine. So for shunt machine with same VT, phi is constant. Why phi is constant? IF is constant, because IF is what? VT by RF. So phi remains constant, flux constant. So once you do that, you will find EB generator and EB motor. So we'll write that for you and also write the answer. So if you solve 4 around, and the motor, for the motor you will find out that it is around 246, I can say 6. So you do around I can say 254 by N1, which is 400, and so N2 I am trying to find out. So N2 is what? N1 into EB2 of the motor divided by EB1. So it is 246 into 400 by 254. Solve 2 more problems, I think. So you see that the starting current, there is a starting problem of the DC machine. So you see that there is the rotor and you have the armature resistance, which is very small, and a motor you directly apply the voltage. So since at starting your speed is 0, so your EB is 0, and your VT minus EB by RA is your IA. Now IA is too high at start, since EB is low. EB is 0, right? So what can you do? You can reduce, you can just one step is to rotate your machine and then provide the supply. What will happen then? If you rotate the machine and then provide the supply, then both the field is there, which will immediately generate EB, and your current is still low. But at starting, you should not plug in the supply. You can rotate the machine through some other means, but that is not practical, right? So you should have some increased resistance at the armature to protect it from getting damaged at starting, and then you have some low field resistance, right? Because to limit IA, what you need? You need more RA and more EB. So more RA means less IA, more EB means less IA. More EB means more IF. More IF means less RF. So more RA and RF should be less. That is a way to start with low IA if you have some arrangements. And the critical resistance of the self-excited DC generator can be reduced by. So you think of this. So the critical resistance line is like this. And if you want to reduce the critical resistance, which is reducing the slope of this line, you can actually reduce the speed, right? So then it will reduce the lower RF critical. So with this I end the session. If you have any doubts, you can just ask in the group, right?